Maybe I should start having the quizzes at the beginning of the class. No, then you would take longer and eat my lecture time. All right, so let's see. What are we supposed to cover today? Any questions on any of the homework? All right, so what I want to cover is I want to cover this last topology, which is the regulated drain current mirror. And I want to go over several different, a few different implementations. And then I want to talk again about the biasing circuits, and this time talk about the short channel biasing circuits. So everything's going well? We're understanding what's going on? Would you say this class is harder or easier, those that have taken 421 than 421? Really? See, I would think drawing the boxes in 421 is pretty easy. All right. So here's the idea. So, well, let me go through the evolution of the current mirror. So we started out with this. Whoops. Something like this. And what was this mirror called? This is just the basic current mirror. Then we went to the cascode, which was this. Righto. Then we went to the wide swing cascode. Which look like this. Keep needing to sneeze. So this is the wide swing. And what was the issue with this? This current didn't match well with this one because this VDS was pinned to what? VDS sat. But this one is VGS, so this current was higher than the current over here. So this is the wide swing, but the currents don't match well. Then we went to the following. Yeah, like this. And we brought this up here like this. And this over. And this was also the wide swing. Better matching. All right, any questions? Everybody it follows, and you can explain why this one, if you're in a job interview, you could explain why this one doesn't match as well as this one. Victor P. So let me explain one more time, okay? So if you look, what controls the current flowing? What's the mirroring action? If I were to point to each one of these and ask, where's the mirroring action occurring? It's occurring here, that's mirrored over there. It's occurring here, that's mirrored over there. It's occurring here, that's mirrored over here. Does everybody see that these transistors, they don't set the current. The ones down here do. All they're doing is trying to pin the VDS more constant. All right, and then here, you still get the VGS is setting the current in each side. However, this VDS is a VGS, and this one is VDS sat. So the current in this side is going to be higher than the current in this side because the VDS of this transistor is higher than the VDS of this transistor. Everybody got that? Okay. Then I say, in order to get better matching, I'm going to try to equalize VGSs. So I add another device up here. I add another device right there. And then that acts to pin this at VDS sat and this at VDS sat. And so I have the VGSs that are the same and the VDSs that are the same. And so the currents in here and here should be much better matched. And the reason I'm using cascoding is to try to keep the voltage across that lower device, drain to source voltage, fixed. Any questions? Okay, so now we're going to, yes?
I don't remember what the 1/4 W rail is.
What the what? That's to pin, so I have a VGS here and a VDS there. So this would generate a voltage which is VGS plus VDS sat. So that I get a VGS drop there and a VDS sat drop there. Now what was the key point about that sizing though?
Because the VGS is higher, so it would keep the same current.
Yeah, it moves it up, but remember we said we could go to say 1/5 for the long channel or 1/10 or even longer. It moves this up and it simply moves that voltage up. And remember I showed you the plot?
Yeah.
And actually I fixed that just in case because I knew there were a bunch of confused looks. So let's go over here, over here, over here. Did anybody check to see if I did this? See the arrow? See how it's behind here? It needs to be brought to the front and then pointed up. And this says that if I increase the VDS, what happens to the output resistance? Goes up. So that's why I use a larger length device there as I push it further up in to this area right here. Any questions? All right. I'm assuming this makes sense. So you know, I want to increase the output resistance, I increase the VDS. I don't need to design it so that this voltage is precisely VDS sat. I can design it so that this is a little bit larger voltage drop and that voltage is higher than VDS sat. I just don't want to go here where I drop where I have two VGS right here and I get a VGS and a VGS. That's just wasteful. Okay? So now here's what we're going to do. We're going to take this, the one other basic current mirror is the regulated drain. We're going to use an amplifier to regulate the voltage right here in the cascode. And I'm going to do this a couple of ways. First is I'm just going to draw an op-amp symbol and we're going to calculate the enhancement in the output resistance. So here's my basic topology. I'm going to have negative feedback. And then there's that. And then I come over here. And what do I want to pin that voltage to? VDS sat. So here's what I'm going to do. I'm going to actually, I'll draw it out and then I'll show you on our biasing diagrams. So I'm going to do, have a current here that goes down, it goes down, here, and then this I'm going to put to a longer L device. I'll just put it like that so you know. Okay. There's my bias. I'm going to come over here. This is where I get my current mirror action. Here and here. Okay. Now this node, what I'm going to do is I'm going to come down here and I'm going to tie it to this, and I'm going to call this VDS sat. Okay, so now what do we know about op-amps? They try to keep their two inputs to same voltage, right? So what does this node get via the op-amp? What does it do? tries to get point to VDS sat. Because the op amp's trying to make this voltage and this voltage the same. Now, what did I call this on my biasing circuits that we went over last time? I called it V low. So that voltage I called V low. Oops. And let's take a look at that in the end of chapter 20. If you look, here's where I pull that VDS sat below VDD out and I call it V high. Here's where I pull it out and I call it V low. Everybody see that? And that's VDS sat. Any questions? So let me qualitatively tell you how this works, and then I'm going to sketch the circuit again here, but simplified. Let's say this voltage is too low. Okay, if it's too low, what happens to the output of the op amp? It goes up because it's going to the minus terminal. So it goes up. If it goes up, it turns this transistor on and then drives this back to where it needs to be till these two are the same. If it's too high, this node then goes low. So let me just pause. When everybody sees if you have a signal going into the minus terminal and it goes up, that means this side goes down. If it goes down, then that means this goes up. Right? And if I'm here, if this goes up, what happens to the output? Goes up. If this goes down, what happens to the output? Goes down. But the takeaway is this amplifier is acting to hold that voltage fixed, to try to regulate that. So now, why is that important? If I, for AC circuit, if I hold this voltage perfectly still, then I'm going to have infinite output resistance. Okay? And I'm going to prove this to you with math. Okay, so this voltage is, for our AC analysis, AC ground, okay? This voltage is what? For AC. AC ground. So I have the following circuit simplified. Now, I'm drawing this as my AC circuit. I have this, okay? So I'm going to say this is a real amplifier with a gain A. So this output is going to be A times 0. This voltage is 0 minus, let's call this Vx. So it takes the two differences and it multiplies them by the gain A. For an op amp, A is infinite. For that, an ideal op amp, A is infinite, which only occurs if the plus and minus terminals go to the same voltage. If they go to the same voltage, this goes to 0, this goes to infinity. Remember, you're in Smith's. How do you explain to somebody why op amps, ideal op amps, have infinite gain? You say, oh, well, when they have infinite gain, that means the two inputs have to go to the same voltage. So you have infinity times 0 so that the output stays finite. Okay, everybody got that? Any questions here? Okay, so now how do I write my circuit? Well, what was the trick? The first thing to note, I'm going to apply a test voltage. We're going to find the output resistance. What was the first thing I need to realize? This is 0, right? So I'm going to replace this with just yay. And then if I look, the top VGS, so this will be GM VGS, which is A times minus Vx. minus, and what's the source voltage? Vx. So this is the gate, this is the source. So the gate is A times minus Vx. The source is Vx. So VGS is A minus Vx minus Vx. Yay? Having a hard time seeing there, Hisham? You know there's seats up here. All right. And then I have my V test, and then my I test, and then my R out. And then the impedance that I see is V test over I test is R out, cascode, enhanced, whatever. Everybody cool with that? So if you had this on a quiz and it was closed book, you'd all be able to do it, right? Sony? Yes? Tell me what to do first. Which one, top or bottom? Bottom? Didn't we do bottom last time? I don't care. Doesn't matter, it's the same thing. Oh, what's the other thing I need to notice? What's the current there? I test. All right, we'll do the bottom and then I'll come back to this. So the I test is going out, and coming in is minus GM times Vx times A plus 1. Just rewriting it a little bit. And then going through here is V test minus Vx all over RO. This is Vt, this is Vx, so Vt minus Vx over RO. Anybody agree with that? Lucas, you agree with that? All right. Should I stop and cry, or is everybody good to move on? Mo, what should I do? Stop and cry? Can you take a web page photo for me? I'll take a selfie with a tear rolling down. All right. So, I don't know. Does anybody not see how I got from here to here? Just in KCL. It's going in as IT, coming out. So that's why it doesn't matter. Coming out, IT, going in, IT. It's on one side, and then leaving or entering is the GM times. Does everybody see the gate voltage is A times minus Vx? Everybody see the source voltage is Vx. So VGS would be this voltage minus this voltage. That's what I have there. I just pulled the Vx out and the minus. Okay, so let's go divide and conquer. So, oh, what else do I need to realize here? Because I've got one equation, two unknowns. What's Vx equal to? Okay, so let's do that. Let's move this over and this over. So if I do that, what I'm going to end up getting is IT times, I'm going to multiply through, let's see if I do too much algebra in my head and you hate me. Okay, this will be R out. This will be plus GM R out squared times A plus 1. Because the R out times the R out, and then the IT over. Huh? So this R out multiplied times IT, so IT R out. This R out multiplied times IT R out squared gives me minus GM R out squared A plus 1. I move it to this side, factor out the IT, and I get GM R out squared A plus 1. I knew I shouldn't have skipped steps. All right, and then last but not least is just the IT times R out. And that's equal to, all right, did I skip too many steps there? Giovanni, is that good? Yeah. All right, I don't want you telling people that your professor can't do algebra. What? So what is R out cascode enhancement approximately then? Well, it's equal to VT over IT. So what is it approximately? So what if A is 0? We don't have that amplifier there. Then that's the output impedance of the cascode. But if I have an A of like 20 or whatever, you see that I could get much higher 20 times higher output resistance. So why don't we pause and do a simulation? Any questions? So the benefit here is if I want a really good current source, then I can use the regulated drain, where what does that literally mean, regulated drain? Yeah, the pin, I'm pinning the voltage here. I'm regulating or pinning that drain voltage. All right, so I'm regulating that drain, and that increases the output resistance. So let's take a look at a simulation, and let's compare let's look at figure 2039. Oh, you know what? Which I think is just moving the, let's just hit run. And then let me find the output resistance, which would be 1 divided by the derivative of that. And you see the 1.6 meg. Everybody good? All right, so now let me show you what I can do just to prove that this works. I'm going to get the scissors out right here. And remember in circuits 1, if you took it with me, how did we fake making an op amp? When I first taught you op amps, how did I fake it? Voltage control voltage source, right? So I'm going to go grab that. And I'm going to go grab this one. And let's call... Actually, you know what? Let's see if we can do it. Killing me. All right. So press G and then wire it up. Let's give it a gain of, how about just 10? And then let's do our little negative feedback. Stretchy, stretchy. Let's go here, here. And where do I connect this?
On the left.
Yeah, right over here, right? Because I want to regulate this voltage. It's not a real op amp. The gain's only 10, right? So I expect the output impedance to go up by 10. Or so. So if I go back now and I look, and I hit this, I say I'm in, take a mental picture of that, 1.5-ish in the middle there, and I hit run, and I see it goes up, not as much as I predicted, but little bit, I guess. Not nearly as much as I predicted. I wonder why. Let's see what happens if we boost that even further. Let's go with, whoops. That, let's see. Converge, damn it. Yeah, so it's basically infinite now. I went overboard, sorry. Run. Yeah, it's going up in the giga-ohms. You get the idea, right? That's going to increase the output resistance. So now, how do I implement this? Or what's the problem is I need, if I do this implementation, I need to add an op-amp to the circuit, right? And that's a lot of circuitry. How can I implement this so that presumably it doesn't take too much circuitry? And the answer is I'm going to show you the simplest way of doing this circuit, which is just use a single transistor for the regulation. But the drawback is, again, you don't get wide swing operation. So, this is page 4. Let's take a look at the following. If I have, here's my bottom cascode, here's my top cascode, then what I'm going to do to provide the gain is the following. So we have our current mirror here, and then we come over here. Oops. And this goes to our quarter length device. And I'm going to show you a sim of this in a second. Comes over, but the way this works is you see this transistor here? If this node goes down, what does it do to this transistor? Yeah, it shuts it off, right? If it shuts it off and that's a constant current, what does it do to this node right here? Causes it to go up. If this node goes up, it pulls this one back up into place. Similarly, if this goes up too far, that turns this on more than this can supply, and will drive this node back down, shutting it off, so that this gets regulated at a VGS. Mo? Good? All right. So let's take a look at this, and this is figure. So the drawback of this simple implementation is that you don't have a VDS sat across that middle or the bottom transistor, you have a VGS. And so if I go back now, whoops, wrong one. And I pull up figure 2042. I see, here's my, and this is to try to regulate the drain voltage so that it matches. Here's my current source from my bias, right click, highlight net. This is my transistor, it's regulating this at a VGS. So what do I expect? This is the minimum voltage I can have here and have high output resistance. No, I need a VDS sat across this, and then this is set at VGS. Yeah, VDS sat plus VGS. So in this process, which the VGSs are 350 millivolts, I expect 350 millivolts at this point, and then a 50 millivolts, so roughly 400 millivolts, the output resistance is going to start to decrease. Let's find out. Right here I said 400, that's a little bit less, but you can see right below that there's not enough voltage across these two transistors and the output resistance goes down. Any questions? You see how complicated these circuits are getting now and the trade-offs that you have? All right, so let's just, for the heck of it, look at the output resistance. All right, much better. 150, 10 meg is much better than 100K. All right, any questions on this? Because I want to go over the bias circuits, then we're going to start on amplifiers. All right, so let's go over the bias circuits. And in this, last time we went over the long channel bias circuits, so this time we're going to go over the short channel bias circuits. And if we start out, what is this circuit right here? Beta multiplier. But what's this in the middle? The amplifier that I use to regulate these two voltages to the same value so that it has better power supply rejection. What is this circuit right here? Startup circuit. What is this for? No, this capacitor. Yeah, what's it for? Stability. Remember, I did this, I took this off and I showed you that this oscillates if you don't, because I've got an amplifier in here. I need to stabilize it. I need to compensate the feedback loop, so I put that there for stability. I got a question for you. If there's noise on VDD, do I want there to be the same noise on B bias P? Yes, you do. Why? Think about it. Here, let me show you the homework problem on that. So let's look here at this one. If I have ground noise, I want the noise on V bias N to follow the noise on ground. Why? So the VGSs don't change. So then the currents stay constant. So I will put a capacitor from ground to V bias N, or I will put a capacitor from VDD to V bias P. But would I put a capacitor from VDD to V bias N generally? No, because I want the noise on ground to be referenced to V bias N. I don't want noise on VDD to be referenced to V bias N, because V bias N is referenced to ground, not VDD. Let's make sure everybody follows that. That's important practically. So V bias P is a VGS below VDD. If there's noise on VDD, I want the noise to be coupled to V bias P so that the VSG stays constant. If there's noise on V bias N, which I haven't used here, or if I use down here, I want that NMOS bias voltages to be referenced to ground. Okay? So now let's go here. So any questions on the top part of the short channel bias circuits? In simple terms, what are these do right here? Notice the V bias P comes from right here. Yeah, they're current mirrors. They're the current sources that go to my long L device and my bias for V bias 4. So it goes V bias 1, V bias 2, V bias 3 for the NMOS, and V bias 4. The V bias 3 is for the cascode. So for the NMOS cascode, I use V bias 3 and V bias 4. For the PMOS cascode, I use V bias 1 and V bias 2 for wide swing cascodes. Okay? For my two VGSs, I call that VN cas. And for my two VSGs, I call that, there's a VSG, and there's a VSG. I call that VP cas. So VP cas is VDD minus 2 VSG. VN cas is 2 VGS. V bias 4 is, what's V bias 4? VGS. What's V bias 3? VGS plus VDS SAT. What is V bias 2? VDD minus VSD sat minus VSG. Anybody get that? One more time. VDD minus VSD sat, and then from here over minus VSG to V bias 2. Any questions on that, Sony? Okay, what is V low then? VDS sat. What is V high? VDD minus VSD sat. So that's a lot of reference voltages, but if I want a regulated drain, I can pick off the V low or the V high, depending if it's a PMOS or an NMOS. If I want a wide swing cascode, I can do V bias 1 and V bias 2. If I need 2 VGSs or 2 VDSs, which I will do, then I can pick off those cascode voltages. Yes? What's that? So this is an amplifier, right? So I need to slow down the amplifier. If it's too fast, then it's going to try to regulate these two voltages, but it's always going to be trying to keep up. Here, let me show you. It's going to say, hey, it's moving too fast. It's like if I drive a car and I try to hold it steady, but I don't know what a good analogy is, but I move a teeny bit, or I see something and I move the steering wheel, and I move the steering wheel a lot and I overcompensate, then I need to pull it back in. So I move it the other way a lot and I overshoot where I'm going. It's to slow down things so that when I move the steering wheel, it slows down the movement one way or another. Slow changes will go through. Yeah, so remember I actually updated this also. That's, we'll just look at the simulation. I updated the file for the, in the beta multiplier for that point. Let me just point you to it. See right here where it says an important note. It's extremely important to understand that together with the benefits of power supply sensitivity are the undesired traits of feedback, that is, potential for an unstable circuit. Okay? And you can go simulate this on your own, where without that capacitor in slowing things down, you get a current that looks like this. All right. Last thing I want to cover on biasing, and I want to, like I said, I want to go over to start on amplifiers. This circuit right here is really useful in op-amp design, and I just want to go over the biasing. You'll recognize the output, if you've taken 421, is an inverter. In an analog talk, this is called a push-pull amplifier, because you can push a current or pull a current. So that when you turn PMOS on, it can push a current out, or you can pull a current back, okay? So if I ask you now, just with what you know, knowing everything needs to stay in saturation, what is the voltage swing on the output node? It can go all the way down to VDS sat, where this can't go into this has to stay in saturation, so I can drop this voltage all the way down so I only have a VDS sat there. Okay, what about how high it can go? VDD minus VDS sat, right? Everybody see that? So that's like as good as you're going to get in an output swing, okay, without doing something really, really fancy, I guess, like boosting or something like that. Okay, so now let's go through. Let's actually see if we can make this a little clearer. That looks better. Okay, so I want you to tell me one more time what these voltages are. What is V bias 1? VDD minus VSG. What is V high? VDD minus VSD sat. Everybody sees these voltages? They come from this bias circuit. The bias circuit's used for biasing those transistors. What about V bias 2? VDD minus VSD sat minus VSG. Okay, now VP CAS. VP CAS was VDD minus VSG minus VSG, or VDD minus 2 VSG. Everybody see that? So I'm using that bias voltage over here, and there's VP CAS, and it's VDD minus VSG minus VSG. And I want half the current. I've got 10 microamps in my normal sizes, so I size this to be half of the 100 by 2 of these two transistors. Why did I do that? Because if I use the VP CAS there and it's VDD minus 2 VSG, then this node goes to VDD minus VSG, and I bias this transistor, and I know its operating point. Does everybody see that? It's a real fancy bias circuit. It's about as tough biasing as you're going to find. Similarly, VN CAS is 2 VGS. So I got a VGS there and a VGS there, and I bias this with a known current, ideally 100 microamps. Then what is V bias 4? VGS. What is V bias 3? VGS plus VDS sat. And what is, one more time, VN CAS? 2 VGS. And notice, since I have 10 microamps there and 10 microamps there, and I need to set this node using this transistor, but I only want 5 through here and 5 through here, I've halved the size of this floating current source here, so that the currents all add up right. And I'll do once in the next chapter at the end, we'll determine what the gain of this is. All right, are there any questions on this circuit? Does it make sense? So you can see current mirror is pretty important in analog design. That's like an understatement. All right, so let's go on to chapter 21, and I want to go through a few things and calculate some gains. What page are we on? We're on page 5. Okay, I'm going to tell you a few things I want you to burn into your brains, okay? First one, if I have a transistor like this, and it's in saturation, you already have that if there's a current and it's biased, right? We already proved that. And everybody can prove that, oh, VDS is greater than or equal to VGS minus V threshold N. V drain minus V source is greater than V gate minus V source minus V threshold N. Sources cancel. V drain greater than or equal to V gate minus V threshold N. But VD equals VG. So that says 0 greater than or equal to minus V threshold N. Yes, in saturation. Everybody can derive that, right? Okay, so the other thing I want you to remember for AC is the following. I'm going to tell you how practically to do this, and then I'll show you tell you, just write down what the exact number is. For AC, what do I call this voltage? VGS, right? And if I ask what is ID, ID is GM-VGS. So VGS over ID is equal to 1 over GM. So if I'm doing AC and I want to replace that with its small signal equivalent, I write it as 1 over GM, where this is the drain and this is the source. So I see that gate drain connected transistor, boom, I say life is good, that's 1 over GM. Everybody see that? Now, when we do diff amps, our load will be a current mirror. What is one side of a current mirror? Gate drain connected transistor. So right off the bat, we know that's a 1 over GM. Now I want to be exact. So what did I neglect in that analysis? What didn't I put in there? RO. Yeah, RO. So all do I do to add RO in now? It's just another resistor in parallel. So I could also say that it's RO in parallel with 1 over GM, which is approximately 1 over GM, just to be exact. It's R out in parallel with 1 over GM. 1 over GM. Any questions? All right, we ready to do our first amplifier? It's going to be tough. We'll see. I'm not going to worry about biasing for the moment. We'll put that in a second. Let's do the following. I'm not worrying about biasing. This is V out, V in. These are small signals. Notice both AC. Okay, I want you to sketch the AC circuit. What is this for AC? How much can I change the VDD with AC? Can't. So what I'm going to do is I'm going to write this. 1 over GML. Looking good? And then here's my V out. And then here I'm going to leave the transistor in. What's the current flowing down there? AC. GMVI. And let's be precise. That's R out in of 1, or let's just say R out 1. And if I want, I can put in parallel with R out L. I'm not going to worry about it. Okay? Would you all agree that I could replace this with a resistor 1 over GML in parallel with R out L in parallel with R out 1 and a current source which is GMVI? Anybody not follow? Anybody follow? This is in parallel with this. And so I've got this current flowing backwards through here, so I'm going to put this as minus GMVI times 1 over GML in parallel with R out L in parallel with R out 1. Or V out over V in equals minus GM times 1 over GML in parallel with R out L parallel with R out 1. Everybody follow that? Any questions? Now I'm going to take this one step further, and I'm going to say that that can also be written as minus or approximately 1 over GML over 1 over GM1. Assuming that the 1 over GM is much, much smaller than the R out, right? And this is the resistance in the drain part of the circuit. And this is the resistance in the source, or looking into the source, and I'm going to prove that to you. It's the resistance in the drain, resistance in the source. That's the gain. And so if I make these similar sizes, what's the gain going to be approximately? 1, or -1 to be precise. Any questions? Let's do another. How about this one? Same exact circuit. I'm going to put a resistor down here called RS. And then I've got V in, and there's V out, and this is VDD, and I want you to find the gain. Tell me what to do. Right, this is 0, so I've got my resistance, 1 over GM. I'm not going to worry about the R outs now. I could put them in if I wanted to. This is 1 over GM load. And now, do I still have VI equals VGS here? No. Here's the VGS. And what's the current flowing through there? It's ID. So I'm going to replace this, and this is where I do it, and it looks easy, and then you get on a quiz, and you're like, what the hell? Okay. I'm going to replace this with GM, M1. I'm going to replace it with VN minus ID times RS. And this is my ID, and this is my V out. Yay or nay? Proceed or stop? Okay, so I get V out. So I'm assuming everybody sees this. Minus ID times 1 over GML. It's minus because it's flowing backwards through the resistor. And that's divided by... I guess we just leave it like that for now. All right, are we good? We don't need that for now. Okie dokie. And so now I have this ID, so I'm going to solve this for ID. And this current, and I'm neglecting R out, but what is this current equal to? What is this equal to? ID. So I get ID equals GM1 times VN minus ID RS. And I'm going to move this to the other side, so I get ID times 1 plus GM1 times RS equals VN. GM1, RS. Oh, yeah. Thank you. Looking good? So now, V out is that, so let's write that on the next page. So I have V out equals minus ID times 1 over GML divided by B in, and I'm going to solve for V in real quick using this, which would be ID over GM1 times 1 plus GM1 times RS. And let me just make sure I didn't make a mistake. B in, M1, ID. Yep, looks right to me. Anybody agree? And there's a reason for this. I'm not just doing algebra. I'm like, man, he loves to do algebra. That's all he does is sit in class and do algebra. That award ceremony I went to on Friday, one of those speakers made a comment like, yeah, you learn that algebra in college and then you never use it again. And I'm thinking to myself, that's not my life, buddy. Anyway, so I cross out the IDs, all right, and then I can write the following. I can write that this is equal to 1 over GML divided by 1 over GM1 plus RS. All right. So now let's compare this to what we just derived. This is the gain, and so with that gate drain connected load, pretty sure I'm going to have a gain less than 1, right? Yeah, minus. But if RS is 0, does that match what I derived a moment ago? Oops. Yeah, a moment ago, with RS equal to 0, I got 1 over GML divided by 1 over GM1. Here, if I put RS to 0, I get the same thing. But this is why I'm doing this, not because I like to do algebra. What we've just shown is that when we have a common source amplifier and we have some resistance in the drain and we can put the output resistance of the transistors in and we have some resistance in the source, that the gain is always the resistance in drain divided by the resistance in the source. So in a source, the resistance would be the resistance I see looking into the source here, which is 1 over GM plus RS. In the drain, here it was just 1 over GM, but I could add the output resistances. So when I'm going through and I'm working in industry, and I want to calculate gains, I don't do math. I just look at the resistance in the drain and the resistance in the source and take the ratio, and I know something has high gain, low gain, and I can estimate what the gains are. All right, I'll do another example. Are there any questions before I do? And then we'll take our grade booster. Why don't we do one with a current source load? Wait, you know what? I went over this and I said to myself, you know what? I bet their 320 class, they really don't understand what common emitter means and common source means. Am I wrong? I am wrong? All right, so let's make sure we understand that. Common source amplifier. And actually, I'm going to make one that is real, that we can build, all right? So if I do that, and let's just say, actually, I'm going to go hog wild here. Call this V bias. What do I bias the PMOS with from our bias circuits? We just went over it, like backwards and forwards. 1, V bias 1. Am I blowing anybody away there? And then I come down here. Now, there's no way I can make two current sources have precisely the same current, so when I put them in series, I got to be careful. Just like I don't put voltage sources in parallel because I can never get one to be precisely the same as the other. The one will end up charging the other, all right? So here's the way I'm going to fake it. I'm going to put a big capacitor here that acts like a short, and I'm going to put a big resistor here that will not load the amplifier. And for DC, all I'm doing is, well, let me ask you, what do I think of this part of the circuit as in my mind? This part. Current source. So I think of this, and let's just use the long channel devices. What was the bias current that we had for the long channel devices? 20 microamps. We all good? All right. And I come down here, and then for DC, what is the capacitor? An open, it's not there. And there's no current flowing into the gate, so there's nowhere for the current to flow. So what's the voltage drop across this resistor? 0. So for this current source to supply current here, then this will go to VG, and this will go to VGS, and it'll go to the precise value needed to sink the current supplied there. Does everybody see that? So for biasing, I'm just thinking of this as gate drain shorted because no current flows in the gate and the capacitor is an open. But for AC, the capacitor is short and the resistor is an open. So for AC, I can do this. If this is my VN, this is my VN, this is AC, I would replace this with what? What do I replace this with? An R out. And then what do I have here? I know I'm doing it pretty fast, but once you start doing it and you read the book, it hopefully will make sense. Okie dokie. All right. So does everybody understand? I think of this for biasing like a 20 microamp current source. For AC, I think of it as just having a resistance R out P. That's the whole point of us spending all that time in chapter 20 and calculating output resistances, so I didn't have to redo it every time I see a circuit. So there's my R out P, there's my R out in. The current flows backwards through them, and so I get V out equals G minus GMV in times R out in parallel with R out P, or V out over V in. I'm going to write it funny for a reason. R out in parallel with R out P. Wait, let me pause. What does the minus sign mean to you in simple talk? Yeah, well, I mean, in simple talk, it means if the voltage on the input goes up, turns the transistor on, and this voltage goes down. Everybody see that? That's what it means to me. Oh, and I didn't explain what a common source amplifier is. Crap. Anyway, that's 1 over GM. So this is the resistance in the drain. Here's the drain part of the circuit. There's no resistance in the series other than what we see looking into the source, and I'll prove to you that it's 1 over GM at some later time. And so it's the resistance in the drain divided by the resistance in the source. So again, I do this because then I can look at a complicated amplifier and go, outputs are out cascode, resistance here, the gain of this is boom. I don't have to do math. Makes me able to look at schematics and calculate gains very quickly. Resistance in the drain, resistance in the source. Common source, what does that mean? So here's the source, right? Here's my output. Here's my input. The source is common with the input and the output. Now, that makes sense, a lot of sense right here because this is at ground. Let's do one for the PMOS equivalent for a common source amplifier. But does this make sense? Common source? Common source have both voltage gain and current gain. So for here, I have the following. This is a common source PMOS. And I'm just going to not draw the biasing. For this one, how is it common source? This is the source, drain, gate. But what is this for AC? It's ground, right? And so if I draw the common source here, it would be plus, minus, plus, minus. Right. Common source means that's AC common source. So now, just real quick, if you notice, this Vn is equal to minus VSG. Does everybody see that? Because VSG is this way, right? So it's minus VSG. And so if you look, the current that flows down when you replace this with R out, V out is equal to this current ID times R out. But here ID is equal to GMP times minus Vn, or GMP times VSG. And once again, when you plug this in, You get resistance in the drain divided by resistance in the source, and it's inverting. The common source amplifier is inverting. Tell me what that means in simple terms again. Yeah, this goes down, this goes up, this goes up, this goes down. Don't think deep. All right, any questions? And of course, if this goes down, what does it mean the PMOS is doing? Turning on. You know, the NMOS gate goes up, it means the NMOS is turning on. All right, so try to read chapter 21, 2. All right, let's stop and do our grade booster.